In this lecture, we'll learn how to classify processes based on the flows that occur into and out of the process, and introduce a procedure for labeling streams in a process flow diagram. As discussed previously, processes are depicted in a process flow diagram, a PFD, by drawing rectangles for key parts of the process and arrows to indicate the inputs and outputs from each part. Processes commonly are divided into unit operations, which are designed to accomplish a desired task. For example, a heat exchanger unit operation heats or cools a process stream. A distillation column unit operation separates the components of a process stream into multiple streams, which are enriched in one or more of the components. In a reactor unit operation, a chemical reaction converts the components of a feed stream into one or more products of higher value. Unit operations use one or more of 5 key chemical or physical principles to perform a task. First, momentum transfer, which is the flow of gases, liquids, and solids. Second, heat transfer, the heating or cooling of a stream. Third, mass transfer, transferring mass from one stream to another. Fourth, thermodynamics, phase and reaction equilibrium. And fifth, physical transformations. These include molding, size reduction, compaction. Symbols are used to represent common unit ops. The symbols for several pieces of equipment are provided here. The most common symbols we will use are those for vessels and columns. We also will simply draw rectangles to represent unit operations. Processes are classified based on the nature of the inputs and outputs. To help identify inputs and outputs, a control volume is drawn around the process or a part of the process. Inputs and outputs are identified by going around the boundary of the control volume and finding the streams that cross the line drawn. The example here has one input and one output. A control volume does not have to be drawn, but it may help to find all inputs and outputs. Even if one is not drawn, we will refer to a virtual control volume in problem solving. The description of the process will provide information regarding values for flow rates and compositions for some of the streams. This stream information may not be complete, but the values provided should allow classification of the process. If the inputs and outputs are continuous, the process is called continuous. If an input occurs, then no input or output occurs for a period of time, and then an output occurs, the process is called batch. The process is called either semi-batch or semi-continuous if it is neither batch nor continuous. Consider filling a tire with air. The tire is a process vessel around which we'll draw a control volume. Going around the control volume, only one input stream is found, the air used to fill the tire. When filling the tire, the airflow is continuous, but it stops when the desired tire pressure is reached. No output occurs. The flow into the control volume is continuous for a period of time but stops. Since the flow is continuous only for a finite time period, the process is not continuous. Additionally, it is not batch, because the continuous flow does occur for a finite time. Hence, you would consider this to be a semi-batch or semi-continuous process. Consider baking a cake. The oven is a chemical reactor in which reactants, the ingredients of the cake mix, react at a prescribed temperature to produce the desired product, a cake. The oven is a process vessel around which we'll draw a control volume. Going around the control volume, no continuous inputs or outputs are found. There is a one-time input of the cake mix and a one-time output of the fully baked cake. Since the input is at once, followed by a wait period, and the output is removed at once, the process is batch. Consider the process used to make pre-cooked pasta. A similar process is used to make a variety of foods, including Twizzlers and Cheetos. The pasta ingredients or raw food is fed to a heated extruder where the ingredients react to produce the desired pasta product. Upon exiting the extruder, the cooked pasta passes through a die to form the desired shape. The extruder is the process vessel around which we'll draw a control volume. Going around the control volume, a single input exists, the raw food which enters continuously to the extruder, and a single output exists, the cooked pasta that leaves continuously. The flows into and out of the control volume are continuous. Thus, it is a continuous process. The most common processes are continuous because production is not interrupted, as in batch processes where production must halt to introduce reactants and remove products. Processes also are characterized as to whether they are steady state or transient. If a process is at steady state, concentration, temperature, and pressure do not change at any point in the process. These variables may vary with position in a single unit operation, or vary from unit operation to unit operation, but do not change with time at any given location. If temporal variations exist, the process is transient. Let's consider the tire filling process. How does the air pressure inside the tire change? Since the pressure increases with time, the process is transient. Let's consider the cake baking process. How do the temperature and composition of the cake change? The temperature increases as the cake mix heats to the oven temperature, and the cake composition will change as the mix reacts to form the cake. Therefore, the process is transient. Let's consider the extrusion cooking process. How do temperature and composition change at any given point in the process? Ideally, continuous processes are run such that process variables such as temperature and composition are constant at any given point in the process to ensure a uniform product is produced. Otherwise, the properties of the product will vary, and customers dislike having a variable quality product. Such processes are steady state. The fundamental physical principle of chemical engineering is the balance equation for a conserved quantity. A conserved quantity is a quantity which cannot be created or lost within a closed system. We'll draw a control volume to define the closed system for which the balance equation is used. A conserved quantity can change form, but it cannot be created or lost. Mass and energy are the conserved quantities which we encounter in chemical processes. The total mass within a closed system cannot change in the absence of nuclear reactions that convert mass to energy. The nature of the mass can change due to chemical reactions, but not the total amount. For example, a reactant chemical species can be converted to a product chemical species in a reactor, but the total mass in the reactor does not change during the reaction. Energy also is a conserved quantity. The total energy of a closed system does not change, but energy can be redistributed just like mass. For conserved quantities, the balance equation for a control volume is of the form accumulation within the control volume equals input minus output plus generation minus consumption. The balance equation often is written in an abbreviated form using the first letters of each term as A equals I minus O plus G minus C. For the equation to be valid, all terms must have the same units. 4 options exist: 2 for batch processes and 2 for continuous or semi-batch processes. For batch processes, the terms have units of mass or moles. For continuous processes, the terms have units of mass flow rate or molar flow rate. Many problems will require converting given stream information to the same set of units. The procedure we'll follow to solve problems is outlined here. Significant time may be required to perform the first 2, as it may not be immediately obvious how the information provided is related to process stream specifications. The last step also may require significant time due to the algebra involved. The first 5 steps involve creating the process flow diagram and representing the given information in a format that facilitates problem solving. We will practice these steps before going through the entire procedure. The first 5 steps are illustrated through several examples. The procedure for labeling streams is to 1. Draw an arrow for each stream into or out of the process. 2. Indicate the amount or flow rate of the stream above the arrow. And 3. Indicate the stream composition, mass, or mole fraction below the arrow. The feed to a batch reactor contains equal molar quantities of nitrogen and methane. To draw the process stream, we start by drawing an arrow. Next, the amount or flow rate is specified above the arrow. The problem statement does not provide any information regarding the amount, so we will represent it by the variable N, which represents the moles fed to the reactor. This variable will be used when we use the mass balance equation. Next, the composition information is specified below the arrow. The problem statement indicates equal molar amounts of nitrogen and methane are fed to the reactor. This implies the mole fraction of nitrogen equals the mole fraction of methane. Since the sum of the two mole fractions must equal 1, 1 is equal to the mole fraction of nitrogen plus the mole fraction of methane, which is equal to 2 times the mole fraction of nitrogen, which also is equal to 2 times the mole fraction of methane. So the mole fraction of nitrogen equals the mole fraction of methane equals 0.5. The stream is fully labeled in terms of known values and variables for unknown quantities. The labeled stream can be used to calculate the kilograms of nitrogen fed to the reactor in terms of the total moles fed to the reactor. From the table of conversions between mass, moles, and composition, the mass of nitrogen fed to the reactor is equal to the moles fed multiplied by the molecular weight of nitrogen. Additionally, the moles of nitrogen is equal to the total moles fed times the mole fraction of nitrogen. Substituting the known values for molecular weight and mole fraction and the variable N for total moles gives the desired results. A stream containing ethane, C2H6, propane, C3H8, and butane, C4H10, flows at a rate of 100 grams per second. The process stream is labeled by first drawing an arrow and placing the known flow rate above the arrow. No information is provided about the compositions. The variables will have to be introduced to represent the unknown quantities. Since the flow rate is specified as a mass flow rate, mass fractions will be used to specify composition. A variable can be used to represent the mass fraction of each component. The symbol X is used to denote mass fraction, and the subscripts E, P, and B denote the values for ethane, propane, and butane, respectively. When specifying composition, always consider the requirement that the mass or mole fractions must sum to 1. For this example, 1 is equal to the mass fraction of ethane plus the mass fraction of propane plus the mass fraction of butane. This requirement implies that one of the 3 mass fractions can be calculated from the other 2. Therefore, the mass fraction of butane is equal to 1 minus the mass fraction of ethane minus the mass fraction of propane. The equation for the mass fraction of butane is substituted in the labeled stream. If an unknown mass or mole fraction can be written in terms of the other mass or mole fractions, due to the requirement that the fractions sum to 1, you must use this expression when labeling the stream. Otherwise, the problem will not be solvable. It's wise to check this for each stream. The stream is fully labeled in terms of known values and variables for unknown quantities. The labeled stream can be used to calculate the molar flow rate of ethane in terms of the ethane mass fraction. From the table of conversions between mass, moles, and composition, the molar flow rate of ethane is equal to the mass flow rate of ethane divided by the molecular weight of ethane. Additionally, the mass flow rate of ethane is equal to the total mass flow rate, m dot, times the mass fraction of ethane. Substituting the known values for molecular weight and total mass flow rate and the variable for ethane mass fraction gives the desired result. Note the conversion between pound moles and moles is the same numerically as the conversion between pounds mass and grams. Additionally, it is assumed you can calculate molecular weight from the chemical formula. This problem statement specifies information for 3 process streams. Attempt to identify the 3 streams by pausing the lecture and reading the problem statement carefully. The first sentence specifies 1 stream. The mass flow rate is given as 1,000 kilograms per hour, and composition is specified as equal parts methanol, denoted by M, and water, denoted by W. This implies the mass fractions are equal. Since only 2 components are present, the mass fractions must equal 0.5. The stream is fully specified, so no variables are required to represent an unknown flow or composition. This reduces the work required in problem solving. The fully labeled stream is shown here. The mass flow rate of 1,000 kilograms per hour is above the arrow, and the equal mole fractions of methanol and water are below the arrow. The second sentence suggests 2 additional streams exist for this problem. The second stream, the bottom product stream, is specified in the third sentence. Its flow rate is given as 673 kilograms per hour, which is the same units as the first stream. If the units were different, a unit conversion would be required to convert to a common flow rate unit. No composition data is provided, so 1 or more variables will be required to represent the composition of this stream. It is anticipated that this stream contains both methanol and water. The fully labeled stream is shown here. The mass flow rate of 673 kilograms per hour is above the arrow. The variable x sub 1 is used to represent the mass fraction of methanol, and the mass fraction of water is equal to 1 minus x sub 1, since the sum of the mass fractions must equal 1. Another variable for the water mass fraction is not needed because of the requirement that the mass fractions sum to 1. The third stream, the overhead product stream, also is specified in the third sentence. Its flow rate is not provided. A variable will be used to represent it. The units of this variable will be kilograms per hour based on the units for the other 2 flow rates. The composition of this stream is 96% methanol on a mass basis. Thus, the mass fraction of methanol is 96 divided by 100, which is equal to 0.96. Since the sum of the mass fractions of methanol and water must equal 1, the water mass fraction is 1 minus 0.96, which is equal to 0.04. The fully labeled stream is shown here. The variable m dot is used to represent the unknown flow rate above the arrow. The known mass fractions of methanol and water, 0.96 and 0.04 respectively, are indicated below the arrow. In the next class, we will solve for all the unknown quantities for the 3 streams in this example. Next time, we'll solve problems using the balance equation for mass that require drawing and labeling process flow streams. Bye for now.